Hello and welcome to this brief presentation related to methods of heat transfer. We will essentially consider the three main methods of heat transfer, that's conduction, convection and radiation. This presentation is designed to underpin future presentations related to heat energy and heat transfer, and also to provide you with a basis on which you can undertake your own further in-depth research into this topic area. Here's a presentation overview. We commence with illustration 1, outlined here, which relates to the various forms of heat transfer associated with a pot that contains fluid which is heated by an external source. Next we define conduction, convection and radiation. Then we refer to combined heat transfer. That is where conduction, convection and radiation problems are analysed simultaneously within a particular problem. We mention the difficulties that can be associated with heat energy calculations, and we also consider scenarios where we want to prevent heat loss from our system, keep as much heat energy as we can within our particular heat engine or production process, and also scenarios where we actually want to expel heat energy from our system to improve the cooling characteristics and thermal efficiency of our system. We use a small case study related to a totally enclosed fan-cooled motor as an illustration within this section. We then briefly define evaporation, another form of heat transfer, and we conclude the presentation with illustration 2, outlined here, which relates to the cooling characteristics of an internal combustion engine. And here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access to the presentation, but please note the times are generally rounded to the nearest minute. Here's illustration 1. This relates to a pot, shown in the sketch here, containing fluid that's being heated. So initially we start with a heat source, and the heat source provides heat to the pot through the process of radiation. We then have the heat circulated within the fluid due to the process of convection, and heat from the fluid is transferred to the handles of the pot by the process of conduction. So essentially those are the three main forms of heat transfer, although in some applications evaporation occurs. This is where the liquid changes its state. So for example, if we add water in the pot, as the water reaches 100 degrees C, then the liquid water could transfer its state into steam, i.e. into the gaseous state. So let's consider the three forms of heat transfer. So firstly, conduction. This is heat transfer due to physical contact. So conduction occurs by heat energy transmission from one part of a substance to another part of the same substance, or from one substance to another substance. Due to the physical contact and without appreciable displacement of the particles, for example the atoms and the molecules forming the substance. The substance under consideration can be a solid, liquid or gas, although heat transfer occurs much more readily in solids and liquids as the particles are closer together. This transmission of heat energy is due to increased vibration, in other words kinetic energy, passing from particle to particle. Metals are the optimum conductors because they have loose electrons within their atomic structure that are able to transmit energy easily throughout the substance. For example, if the tip of a poker, that's basically a metal rod, is inserted into a fire, the molecules are caused to vibrate more readily, and thus heat travels along the poker from the tip to the handle. Let's consider convection. This is due to the movement of the fluid. So transfer of heat energy within a fluid, that is a liquid or gas, occurs by the mixing of one portion of fluid with another, as the particles are free to move around. If part of a fluid becomes heated, then expansion occurs and the fluid becomes less dense than the surrounding parts, and so the heated particles rise. These are then replaced by surrounding colder particles due to the effect of gravity. Remember from our previous presentations, density is defined as mass divided by volume. If the mass remains constant but the volume increases, then obviously the density reduces. Here's a recap of the mass density formula, symbol ρ. Movement of the fluid occurring due to changes in density is termed natural or free convection, whereas movement induced by mechanical means is termed forced convection. For example, a fan heater which blows air over an electric element is considered to be forced convection. In other words, it's not naturally occurring. Let's consider combined conduction and convection. The transfer of heat energy through solid bodies is by conduction only. However, the transfer of heat energy from a solid surface to a fluid occurs partly by conduction and partly by convection. Whenever there is an appreciable movement of the fluid, the heat transfer by conduction, that is through a thin boundary layer of fluid contacting the surface, into the fluid is negligible compared to the heat transfer by convection. Let's consider heat transfer using radiation. That's when there is no physical contact between the substances or bodies. So radiation emanates from all bodies at all temperatures above absolute zero. That's 0 K. But the higher the temperature, the greater the amount of energy radiated by a body. Radiation is the transference of energy from one place to another in a form that can be described by electromagnetic waves. These waves do not affect the medium through which they pass. The waves can be reflected, in other words, not absorbed. They can be refracted, i.e. can change the direction, and they can pass through a pure vacuum. Radiation continued. If two bodies at different temperatures are positioned so that the radiation from each body is intercepted by the other, then the body at the lower temperature will receive more heat energy than it is radiating. And so the internal energy of the initially cooler body will increase, whilst the internal energy of the higher temperature body will decrease. Hence there is a net transfer of heat energy between the bodies due to the temperature difference by the process of radiation. Examples of some familiar radiation sources include the sun, microwave ovens, power lines, radios, and I'm sure you can research many more examples. Let's consider for a moment combined conduction, convection, and radiation. So in practice, heat energy may be transferred by a combination of conduction, convection, and radiation. And the engineer endeavours to assess the effects of each mode of heat transfer separately and then summate the results. Generally, the main types of problems with such heat transfer calculations include the following. 1. Determining the required heat transfer of energy to or from a fluid for a given process. For example, when analysing a boiler, heat exchanger, or condenser. A second type of problem relates to where heat loss is a disadvantage to system performance. In this case, there's a need to prevent heat loss from a fluid to its surroundings. For example, we might require a constant temperature for a particular industrial process, so we need to avoid heat loss from pipes, etc. Preventing heat loss will reduce energy costs and also can improve the working conditions of a particular workshop. And problem type 3, this is where heat loss is an advantage to system performance. So in this case, we want to design our materials and system to be efficient at expelling heat energy from a fluid to its surroundings. This might be the case in a petrol engine. It runs very hot, so we want to try and keep the engine cool by dissipating the heat from the engine. The cooling requirements for a totally enclosed fan-cooled electric motor also requires the efficient design of the casing and the airflow to try and expel as much heat as possible from the electric motor to prevent it from running too hot, as this affects its thermal efficiency and performance, and also can cause premature failure of component parts such as bearings. For background information, here's a few notes related to totally enclosed fan-cooled motors. So totally enclosed fan-cooled motors, acronym TEFC, electric motors, illustration shown here at the top of the slide, are a type of industrial motor having an enclosure that does not allow outside air to freely circulate through the motor's interior. The ideal motor, sometimes termed a drip-proof motor, would have open vents within the casing that would actually allow air from outside the motor to flow directly through the inside of the motor, as this provides the most efficient cooling characteristics. Such TEFC motors are the preferable choice for wet outdoor applications or indoor locations where regular washing of equipment is required, for example, within the food processing industries. TEFC motors have an externally mounted fan that blows outside air over the motor's finned frame to facilitate cooling. Here's an exploded view of a totally enclosed fan-cooled motor. This is sometimes termed the stator frame, shown here, and you can see the finned casing shown here in the diagram. Just note for reference that the fin construction is used to generate a larger surface area and thus allow for greater heat dissipation and thus greater cooling of the motor. There are brackets rigidly bolted at either end of the stator frame, and although it's not easy to clearly see on this diagram, there is a fan located at the rear of the motor on the outside bracket. The fan is shown here, which rotates with the rotor assembly and blows air over the fin motor frame to facilitate cooling of the electric motor. Heat is generated internally from the rotor and stator windings. The stator windings, for example, are shown here. And this heat is transferred to the enclosed air using convection. The internal heat is then transferred through the motor's casing by conduction. And as stated previously, when the outside air is blown over the motor finned casing, heat is then transferred by both convection and radiation to the surroundings. This external cooling is essential for the TEFC motor, as the hotter the motor operates, the more its efficiency and performance degrades. And also there is an increased potential for earlier component failure, for example, the bearings. So that's just an overview of the TEFC motor as an illustration of the various methods of heat transfer through its system, and also a useful illustration of why we need to expel heat during its operation. So as you can see, heat transfer problems can be quite complicated when considering an array of different industrial contexts and applications. Let's briefly consider evaporation. A hot liquid also loses heat energy through evaporation. This is where a fluid transitions from a liquid state to a gaseous state. In this process, faster moving particles escape, leaving behind a liquid in which the average kinetic energy of the particles are less, and therefore the temperature of the liquid has been reduced. And our final illustration, illustration 2, this relates to the internal combustion engine, diagrammatically shown in the sketch. This is a 4-cylinder piston engine. Here are the 4 pistons at various stages of their cycle. This is the cylinder block, usually a cast iron block. And the main type of problem here for the engineer is to try and keep the engine cool. So we want to dissipate as much heat energy as we can. So we consider one cylinder and piston here. We initially have conduction of the heat gas within the cylinder, and that conduction occurs through the cylinder walls. We then have fluid circulating, often termed a coolant, cooling water in this case, circulating around the piston. So the water film in contact with the cylinder through the process of conduction will then start warming the coolant or the water, which induces the process of convection within the cooling water. The cooling water then passes, as shown by these blue areas, through the engine, eventually passing through the radiator shown here, and then through the process of radiation, heat is then extracted from the water and transferred to flowing air through the radiator, and thus cooling the fluid, which can then be circulated back into the cylinder block. So again, another example of where we have conduction, convection and radiation within our system. Here's the bibliography used to help generate this presentation, which I hope has been of interest to you and does help underpin your knowledge for slightly more advanced work relating to heat transfer calculations. Thank you for viewing.